Hello everyone, I'm Abdelrazak Khroubi, a PhD candidate at Geomatic Unit of the University of Liège. The paper I'm presenting is entitled TESSERAE3D, a benchmark for Tesserae Semantic Segmentation in 3D Point Cloud, which is the first benchmark for Tesserae Semantic Segmentation. It is a joint paper with Lynn Van Versch, Roland Bilin, and Florent Poux. The talk is structured as follows. First of all, I will introduce the context of the paper and the related work. I will continue by presenting the TESSERAE3D dataset, then a semantic segmentation baseline based on machine learning algorithm. And finally, I will present the result, discuss them, as well as show the direction of future works. The present work is a part of the research project named PROMON. This FNRS research project investigates in the production of mosaic in the north of the Carolingian Empire, and it takes as case study the mosaic of Germany-des-Prés. This Carolingian oratory situated in Germany-des-Prés, Loiret, Centre-Val de Loire in France, hosts a very old mosaic dated from the 8th century. It is a unique opportunity for the study of mosaic and also their specific material. In general, mosaic are considered decorative art formed by individual entities called tesserae. They are usually of cubic or irregular shape and made of stone, glass, ceramic, metal, or other organic material. These tesserae are assembled using mortar to obtain pattern and figure. The mosaic of Germany-des-Prés is composed of approximately 100,000 tesserae, composed of tesserae from different material, size, and period. It is a well-preserved and restored mosaic that culminates at 5.4 meters above the ground, presenting many challenges for 3D capture from both active and passive sensor. Our main purpose was to individualize each tesserae to attach some key information, mainly its composition and material, its place of origin, its dating, and state of conservation. Related to this task, which is Tesserae Semantic Segmentation, existing research on the topic is carried only on 2D images. For example, Alberto Bartoli presented a completely unsupervised approach which consists of a deformable model to overlap the mosaic and adapt the actual shape of each tesserae using genetic algorithm. Felicity also created a mosaic segmentation algorithm based on unit deep learning network coupled with image processing technique for refinement such as hierarchical watershed algorithm. Other work in mosaic segmentation using 3D point cloud has tried to get around the lack of training data by adapting an unsupervised clustering process for segmentation and a reasoning ontology for classification using user-specified rules. However, for semantic segmentation using supervised approach, there is, to our knowledge, no existing open source point cloud dataset. So, we propose to extend the few existing mosaic segmentation approaches, especially over 3D point cloud, by providing two things: a point-wise labeled mosaic tesserae point cloud dataset and a standard baseline for segmentation using random forest and gradient boosting multi-classifier. First, TESSERAE3D was acquired by a phase-based calibrated terrestrial laser scanner, which is merged with dense image matching. The result covers approximately 9.3 meters square and consists of approximately 500 million points, which represent an average density of 54 million points per meter square. A classification for the census of the main type of tesserae was made based on the expertise of archaeologists as well as on the sweep of all the mosaic to identify this type of tesserae visually based on properties which are mainly the color, the type of material, the shape, and the size. An unclassified label is used to only focus the evaluation on the portion of the point cloud that has been classified only, which represents until now 30% of the total mosaic. The point cloud is classified in 10 labeled tesserae types, plus one label for mortar and one label for unclassified part. And it contains 7 attributes, which are XYZ, position of each recorded point in local coordinates, RGB, natural color reflectance of red, green, blue as an integer from 0 to 255, and label, which is the class of each point recorded as an integer from 0 to 11. This manual annotation was performed using the segment tools within the open source software Cloud Compare. And these are the result of the manual annotation. The picture shows the annotated part of the mosaic, which cover all tessera types, and the distribution of the classified parts show a predominance of the old golden tessera and mortar, but this number will change and will be updated. Second, here we provide a starting point for multi-scale semantic segmentation using random forest and gradient boosting classifier. So, starting from our point cloud, which is split into labeled data and unseen data, we choose different spherical radius to select neighborhood point, which will be used to extract a geometric feature using Cloud Compare software. After that, we select the important feature which contribute the most in the classification result. Finally, after creating and validating our predictive models, we process the unseen data for classification. And now let's detail the part of feature selection. In fact, the objective of feature selection is to reduce the potential redundant feature and noise, and also to speed up the calculation and identify a small set of discriminative features that can still achieve a good predictive performance. In our case, we use the embedded selection method considered in the random forest classifier. For radiometric feature, we selected red, blue, green, and the average of the tree channel. And for the geometric feature, we selected surface density, linearity, planarity, and omnivariance, each one with its specific radius. And as a classifier, we used the random forest classifier, which uses bagging as an ensemble method and a decision tree as an individual model. And we used gradient boosting, which is another type of machine learning multi-classifier. It relies on the intuition that the best possible next model, when combined with previous model, minimize the overall prediction error. And to evaluate the performance, we summarized the metrics in the table below. We used a weighted averaging, so for each class we calculated metrics and find their average weighted by support. And we can see that the gradient boosting outperformed random forest and achieved an F1 score of 89%. But in this study, results are for baseline illustration purpose mainly, and better results could be potentially achieved by further parameter tuning. Also, with unbalanced data, which is our case, we recommend confusion matrix as a good practice for summarizing the performance of the classification algorithm. In the right table, each column represents the number predicted to belong to the class, while each row represents the true number that belong to the class. And for each intersection, we provide two normalized values in percentage, the first one for random forest and the second one for gradient boosting. Variable importance assessment is also another interesting aspect to study, as we identified the most important predictor were RGB channel and surface density, which show the importance of the 3D geometric feature over 2D feature, RGB. And to conclude, in this work presented TESSERAE3D dataset. With this dataset, we aim to participate in bridging the gap of the large lag in training data point cloud for complex and specific cases. And the goal is to reveal the full potential of machine learning model in the semantic segmentation of decorative art and especially mosaics. Many directions can be studied in future work. First, we aim to create a Tesserae-based segmentation. Second, we aim to make available an enhanced segmentation dataset where each TESSERAE is individually separated with TESSERAE-based evaluation matrix. And finally, to test more other model for semantic segmentation. That's all for my presentation. More details are available on the paper and the GitHub. Thank you so much for watching, and we look forward to your feedback and question. Thank you.